right, let's start. So today's going to be more divide and conquer. I think all week is still divide and conquer. The two examples we'll look at are selection and closest pair. But before that, now that we've had a week under our belt, maybe have more feedback about the syllabus, stuff like this. Uh, is everything okay? People know where their PSOs are. Any early feedback, etc. Any questions about the syllabus? Hey, everyone found EdSTEM? I don't really know how it works, and just kind of put a link out there and hope you can sort it out. Okay. All right. Then let's do the fun parts. Okay, so our setup for this problem is going to be a little bit like sorting. I'm going to give you an array of n comparable elements. Okay, not sorted, just in some arbitrary order. But instead of trying to sort the whole thing, we're trying to pick out some particular element. Like maybe you want to find the median out of this array, or more generally, the kth smallest, the kth largest. So k smallest is called the rank k. Maybe it's number 100, number 200, whatever. But you're trying to pick it out. Okay. So let's take this example here of 10 or 11 numbers or something. What is a median of this set of numbers? I don't actually know, so I'm kind of trusting you. Yeah, what you get? 64. Anyone else get 64? Yeah? Okay, so median should have the same number below and above. So let's see. This is smaller. That's not smaller. Smaller, 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 smaller. So we have 5 that are smaller, 5 that are, oh, 56. Oh, is 64 actually the median? No. Okay, what else is the median then? Yeah, 56. Okay. Then we have uh 5 that are smaller and 1, 2, 3, 4, 5 that are bigger. Okay. All right, but at least that illustrates that it's non-trivial to find the median even out of a relatively small list. Okay. Now, what is sort of the most obvious algorithm for computing the median, especially based on what we've already done? Yeah. Yeah, so the natural thing is to just sort them all and then pick out the median or whatever rank you're going for, and that'll take n log n time. Okay, so our goal today is to do better. We're going to try to do better than n log n because you don't really have to have them all sorted to figure out the median. Okay, so, well, we're going to make a recursive algorithm. So as I do, I was first going to try to solicit it, you know, some recursive spec. So I've already chosen a name, select is easy enough. And we basically want to state the input, the output, that kind of thing, but sort of figure out what we want to implement and in particular what we can call recursively. All right, anyone want to take a stab at it? Okay, I'll lower the bar. Maybe you don't want to, but you're still willing to take a stab at it. Okay, let's put the input A in there. Yeah, 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 this rank K. Okay, good. So those are our input parameters. And now we just have to describe kind of what the input is and what we're trying to return. Yeah. Yeah. Return, I don't know, rank K element. Yeah, I'm not sure if it's worth pointing out maybe of comparable elements, but this general thing. Okay. Something like this. It's not so deep. We are basically just restating the problem in this case. Sometimes there's a bigger gap, but in this case, it's doesn't require too much creativity. Okay, good. But at least we kind of know what we're implementing. We also know what we can use recursively. So, all right, so our goal is to get a linear time algorithm. And I was going to try to figure out how to do this rhetorically so you can kind of guess a lot of the parts. So, as a warm up, suppose I give you a linear time subroutine to get you the median. So that's a special case, right? It's particularly rank n over 2. So suppose I gave you a subroutine uh, to compute the median. Now you want to use that to figure out sort of general selection. All right, any ideas? Yeah. Okay, do some kind of binary search. So what would be like the first step? Okay, so we get the median, and then okay, so if k is less or greater, and then we go to the appropriate side. Now, what does go to the appropriate side means? We're gonna have to assemble some input or something, right? Yeah, but what is that side? So you get the median. What do you mean by that? Well, let me be more specific. Uh, okay, so you have this huge array of like unsorted elements, right? And your subroutine would say, oh, this element here in this random slot of the array is your median. So when you say recurse on one side, do you mean recurse on all these elements? On all the smaller elements, which means you're going to want to go and compare everybody else to the median to figure out who is smaller than the median and who's bigger than the median. So yeah, you're going to want to recurse on the bigger or smaller, but there is a little bit of assembly required. Okay. So first of all, sometimes when we think of kind of splitting like this, a terminology that's commonly used is a pivot. Okay. But here I have a picture for us. Okay, so step one, we'll find a median. And then we're going to divide the input into everything smaller and everything bigger. In principle, with the median, these should be equal size. Somehow it doesn't quite look equal, but it's a theory course. Use your imagination. So we divide the input in two halves. And then based on whether this rank you're going for, k is bigger or k is smaller, you're going to recurse on the appropriate side. And then a recursion will do things correctly. Now, I want to be a little bit careful. So when we recurse, the two inputs are a and k. So I think we all agree that, okay, if I go on the left, that will be a in red in green. If I go to the right, blue will be a. But what about the k parameter? So if I go on the left, k is less than n over 2. Should I keep the same value of k? Yes, okay. So if I want the 10th smallest, and there's 10 is still on the left side, I still want the 10th smallest. But what about the right side? Yeah, so if you wanted to rank k overall, but now you're looking just amongst the blue, you want to subtract out everything you removed. So you want to update k to be something like k minus n over 2 or something. Being careful about that fence post error. So that's one thing to keep in mind. So the pseudocode might look something like this. As usual, I feel like this makes it look more complicated than it really is. But here we get our pivot by just computing the median. If we are looking for the median, we're just done. We can return it. Otherwise, I sort of did this implicitly, but you want to assemble the array of everything smaller and either recurse on the left, same value of k, or you want to assemble the array of everything bigger. And here I'm going to subtract that n over 2 from k. Okay, because the rank is kind of relative. Okay. So I think nothing too deep or anything. If you took your time, you wouldn't make this mistake, but if you're rushing, then you might skip that detail. Okay, so if we're to model this idealized algorithm, of course, there's some gaps here because we don't necessarily have a linear time subroutine for the median. But if we're going to model this, then well, let's figure out the running time. So uh, how can I model this as an equation first? Yeah. Uh-huh. Uh-huh. Perfect. Right. Okay. So do we have a recursive call to half the input? Plus, we need to spend linear time to assemble the arrays. Also, we're assuming that that median findings subroutine also took linear time. So there's two sources of linear time. So we'll get something like this. Okay. What does this kind of running time come out to? Yeah. O of n. So even if you did, recursion tree isn't super interesting because there's not much branching. But you have a problem of size n, a problem of size n over 2, a problem of size n over 4, n over 8, all the way down to 1. And each of these are generating linear work. So like n over 2, I'm just repeating, of course, n over 8. And then what does this all add up to? Some big O of n. Okay, maybe 2n or something, 1/2 plus 1/4 plus 1/16. That'll get you just 1, right? Okay. Now, good. So if you had a linear time algorithm for median, then actually you can get any general rank completely. So at some level, the things are equivalent. Of course, if you could do general, then you can get the median, but this is saying if you had the special, you can get the general as well. So let's keep going. So obviously we don't have a linear time median subroutine, which we now know is as good as solving the problem. Okay. So here's maybe the next relaxation. Okay. So now suppose you had a linear time subroutine that doesn't give you the exact median, but a certain kind of approximate median. Okay. Suppose I gave you something that takes linear time. I'll call it APX median. APX for approximate. Okay. And it won't return the median, but it'll return something that's in the middle 80%. So the rank will be at least n over 10, and it'll be at most 9n over 10. Okay, so it's going to leave out the 10% on the extremes. Okay. So suppose now you had this weaker subroutine, but still takes O(n) time. How might we revise our algorithm? How can we use this subroutine instead? Any ideas? Yeah. Did you just use approximate median instead of like the full median function, and then just the recurse on like whatever parts like you pivot based on like median approximate? Yeah, can we basically do the same algorithm? Well, you sure can. It's a free country. So let's just do the same thing and see how it works out. This is the same picture. It's not so interesting. You divide the input on the approximate median. It's not necessarily even on both sides. And then we'll recurse on the appropriate half. And then recursion will always get the right answer, right? Smaller input. Okay, so good. Um, so this is roughly the same code as before. There's only one thing I want to point out. Before our pivot was always the median, so we always knew it was rank n over 2. Now we get some approximate median. We actually don't know the exact rank right away. So we'll spend a little bit time comparing p to everyone else to figure out its rank. You already are comparing anyway to get the two halves, but you do need to figure out its rank, and then you'll compare, you know, that pivot's rank to what you're going for. If it turns out to be the same, you're happy, you're just done. If it's smaller than your recurse on the left, If it's bigger, you'll recurse on the right, just like before. Okay. So now, L can change. It's not always n over 2. Okay. Roughly the same algorithm. Okay. So now what would the running time look like? First, let's just model it. What would the equation be? Yeah. Yeah, exactly. So maybe the only point you hesitated was that it wasn't exactly n over 2 this time. N over 2, of course, that's very straightforward. Now it could be n over 10 or 9n over 10. But in general, we're trying to do worst case analysis. Okay, so we're gonna be pessimistic and conservative and say, well, in the worst case, I still get rid of 10% of my input. Okay. So the worst case is like you're at the very edge, you get some median at the very edge, and it's on the bigger side. Okay, but you're always going to guarantee at least 10% uh, of your input. It's the same thing. And we can do similar calculation as before. The first problem is going to generate n work, then 9 over 10 n work, then 9 tenths squared, 9 tenths cubed, and sum all the way down until you get down to 1. Okay. All right, so this is not as easy as just summing halves that are decreasing. Nonetheless, what will all this add up to? Yeah, O of n. So any constant less than 1 is still just going to give you a leading constant, some constant. Okay, so it's 0.999999999, and then you're doing 0.9999 and then 0.999 squared and 0.999 cubed and so forth. You'll still get a constant. That constant will get bigger, be like 1 divided by 1 minus 0.999 or whatever, but it's just a constant. And we're all friends in big O notation. Okay, so we don't have to worry too much. Now, oh, right. So it's big O events. Okay, so actually, so what we've shown is that, okay, it might seem we didn't give up much when we moved from a perfect median to an approximate median. In fact, all that really mattered is that we were able to chip away a constant fraction of the input, right? If 9 tenths was 99 over 100 instead, that's a weaker subroutine, but it would have been just as good for our calculations. Okay, so that's kind of interesting because at some level, you might hope that getting an approximate median is easier than getting an exact rank K thing, right? Because the approximation gives you some wiggle room. Okay, good. All right, so it remains to try to implement something like APX median. Okay. So the point is that we have a bit of a relaxed subroutine to try to figure out. Does anyone want to give it a try? This is where the algorithm starts to get ingenious. Not ingenious. So it's a little harder to guess what the ultimate solution is, but still, it's more fun to try before I tell you the answer. Yeah.
This might be kind of dumb, but like if you look at number of elements equal to like n over 10 plus 1, you just pick the like out of the smallest or median of both those, then you probably get something.
Oh, okay. So yeah, okay. So here's your whole array of input, and you're saying, okay, let me look at like the first 10%. Not necessarily the smallest 10%, just the first 10% that appeared in my array. And then let me get the median uh, of this part here. Okay, so you figure out the true median of your small input. Okay. And now, what is it to the rest of the?
Like between 1/10 and 9/10, and like if that part is like the 10% like biggest number, say there, you're still gonna get.
So you are guaranteed that roughly 5% will be on either side, although not necessarily 10%. But of course, we could have made that twice as big or something, right? So maybe if I won't redraw it, I'll just say this was 20% all along, and you get the median out of your 20%, then you're guaranteed something in between that at least gets rid of 10% for you, right? So you could just try to look at a smaller input, recurse. Your exact median on the smaller input will be an approximate median of the overall thing. right? So if you have 20% and you get the median of that, there's 10% smaller, 10% on the other side. So even if this thing you found turned out to be very extreme with respect to everything you didn't look at, you'll still get rid of 10% on one side or the other. Okay. So if I wanted to model this running time recursively, what would our equation look like? So there's going to be a big O of n. Okay, so just to be clear what the algorithm is, we'll first compute the median basically recursively over 150 input, 20% of the input. And then we're going to use that, and then we'll separate into two halves just like before and recurse on whichever side we're supposed to go on. Okay. So how should we model the running time? Yeah.
Just T of n over 5.
Okay, so that first recursive call is T of n over 5, right? That gets you this pivot here. Then you compare everything to your pivot, and then that's going to split your input. And then you're going to recurse on the left or right or whatever, right? So what about that second recursive call? How should we write that out? Yeah.
T of n.
Oh, sorry, I missed. Who was that? Oh, okay. T of n over 2? Okay, so you should be a little bit careful about T of n over 2 because just because you're the median of your 20% doesn't mean you're the median overall. N over 2 would be great, but you're not promised that. What's the worst? 9n over 10, sort of like before. Something like this. Okay. So this is to get your median of the 20%, and this is to recurse. Okay. All right, so let's solve this recurrence tree. Let me put this on the side. Okay, so originally, you have a root with size n, and then you're going to branch out into one problem of size n over 5 and one problem of size 9n over 10. Okay, and that's going to branch out further into like n over 25, and then this will be, gosh, 9 over 50. It should sort of be the same, 9n over 50, and then 81 over 100n. It's just from branching again. Hopefully I did that correct. I'm liable to do it wrong. And so what would the work starting to look like? So at the top level, it's linear work for each problem, excluding the recursive subcall. So you spend n on the first one. Okay. Well, how much work do I spend though on the second level? Yeah, 11n over 10. I'm going to write it this way. 1/5 plus 9/10 times n. Okay. What about the level after that? The addition might be getting a little harder. Basically, what does that third row add up to? Sorry? Ish? Okay. Here's, I'm going to be lazy, and you tell me if you agree. It's going to basically square it. Okay, so you can kind of see the squaring happening, right? You have 1/5 squared, you have two 1/5 times 9/10 terms, then you have your 9/10 squared. Okay, that might make it a little bit easier to guess what the next row would be. And so forth. Okay, so all put together, you're going to get something like, maybe I'll ask you how many levels. Maybe you'll start from 0, 1/5 plus 9/10 to the I times n. But how deep will the tree be? Yeah, but so it'll be log n-ish, but here the base is going to matter. Yeah. Log 10 9. So you're always getting rid of 1/10 of the input and keeping around 9/10 in the worst case. So this will really be like log of 10 over 9 n. Okay. All right. So now this theory is actually a little bit messier compared to before. Okay. Anyway, what does this sort of evaluate to? As you can see, my live handwriting is not as good as my prepared handwriting.
The overall n squared. I mean,
Sorry?
it's got n squared.
Overall n squared, you believe.
I mean,
So it's going to be bigger than n. So why first will it be bigger than n?
because the factor like the series is greater than one.
So this is a geometrically increasing sequence. Okay. So we can't just say, oh, it's a constant. Do we know roughly how to do this? I know you probably are thinking of some Wikipedia. Yeah.
Since like the ratio is greater than one, you just take the biggest terms.
So it's always going to be dominated by the biggest term. So there is a more exact way to do it, but you don't need to do it in this class. So you're going to get, 1/5. Maybe I should write 11/10. 11 over 10 to the log 10 over 9n times n. Okay. Now, this is a little bit awkward, of course. It would be very nice if we got some polynomial in n, n to the 1 point something, n squared or something like this. How can I take an expression like this and get a polynomial in n that's kind of easier for us to think about? Yeah.
You could switch the 11 over 10 to the n.
Yeah, so you can basically switch the 11 over 10. How do we do this? Okay, so I'm always very well, I forget everything. So what I would do is I would write this 11 over 10 as 10 over 9 to the log of 10 over 9, 11/10. I didn't allocate space very well. All right, enhance. Okay, let me erase this. So, I mean, this is just like the rule of logarithms, right? I'm replacing 11 over 10th with 10 to the 9th to the log base 10 over 9, 11/10. And then we still have this log 10 over 9n here, right? Now, here we're just multiplying two terms, and you can always switch the order. So I can imagine this being on the inside and that being on the outside, right? But now what's 10/9 to the log 10 over 9n? N. So now it's easier to I'll go this way. Then you're going to get something like n to the log 10 over 9, 11/10. Okay. So in that way, you're able to bring the n down. I know there's like a more slick rule just, inlining this, but I always forget it and I'm afraid to kind of misrecall it in a lecture. So if you do it slowly, you can always do it this way. Okay. Now let's not forget this n over here, that will go here. Okay, so it'll be, or you can write it up here, n to the 1 plus, because there's always that n all along, besides whatever was coming from that increasing sequence. Okay, so you get n to the 1 plus something. I don't know what it is, but you can Google it or calculate it, right? But actually, this is actually slower than sorting, because there's some polynomial bigger than 1, and before we could have done n log n. So it's not a bad idea. I think this actually was suggested last year too. But the way it works out, the real problem, I was about to curse, is really that n over 5 plus 9n over 10 is giving you more than n, and that's branching out into this geometrically increasing sequence in the recursion tree. That's why we end up with this superlinear running time. Okay. Well, there's not much white space left, but does anyone want to suggest any other ideas? It's at least fun to explore things before seeing the answer. Yeah. Okay, so what if we had instead of 20% done like 50%? So this will go up from n over 5 to like n over 2. And then this will go down, I think, to like 75% of n. And you're still going to end up with something adding up to more than one full n. So I think no matter what you did it within this strategy, if you instead of 20% you had done more, or if you had done less, I think you'll still come up with the same arithmetic kind of conclusion, which is that actually your levels are getting bigger and bigger in the recursion tree. But it is worth exploring. All right, any other ideas? Just for fun. Okay. And without further ado, okay, so we're going to try something called the median of medians. Almost as exciting as the algorithm itself is like just how famous the set of authors came up with this is. So Blum, Floyd, Pratt, Rivest, and Tarjan. So between them, you have 4 Turing Award winners. And then the only one who didn't win the Turing Award was sort of like a founder of Sun Microsystems. So Pratt did pretty well too. The real question is, would you rather have a Turing Award or a big company like Sun Microsystems? Okay, so and some of those names, Tarjan's going to come up a lot. Blum and Rivest might too. Oh, Floyd's going to come up very soon. Okay, so here's the idea. So you have your big input array. Okay, and what we're going to do is we're going to break it up into groups of 5. Okay, and we'll compute the median for each small group of 5. That only takes constant time to compare 5 numbers. Okay, so for every group of 5, you're going to find the median, and you'll collect all of them. Okay, so now you have something that's only 1/5 the size, because for every group of 5, you've taken 1. And now you're going to find the median recursively out of this smaller input. Okay, so this is another way you try to get an approximate median. I'm first going to try to collapse the input roughly by a factor of 5, for every group of 5 getting to that baby median that's easy to find. And then I'm hoping that by getting the median of here, it'll be some approximate median of the original input. Okay. And somehow we're hoping that, so this is in some ways similar, right? It is ultimately computing a median over 20% of our input, which is very similar to what we were just doing. Only the way it's assembling that 20% is not as arbitrary as before. It's doing this median of medians. Okay. All right, so, okay. So our claim is that if you do this median of medians thing, then your rank will be somewhere between 3n over 10 and 7n over 10, plus or minus a few, just because it might not divide by 5 evenly. Okay. But the claim is you're going to get a pretty good median out of this median of medians. This is the better kind of better bounds than we got before, which was just n over 10 on each side. All right, so good. So here's what we're going to try to do. So, okay, imagine taking this kind of green array of the medians, and let me first kind of lay them out from left to right so that they're in increasing order. I mean, I just want to give a visual proof. So imagine we had rearranged this, okay? And then I'll lay out all the groups of 5 that they came from. But the groups of 5 will also be listed in kind of descending, increasing order going from top to bottom. Okay, so I've kind of taken our big array, and for the sake of the proof, the algorithm doesn't literally do this. I've rearranged those groups of 5 so that the medians are in increasing order. And then I've also kind of arranged those individual groups of 5 so that you can see the median in the middle vertically. Okay. All right, so good. So that's that. Now, we want to show that the thing we return, which is the median of medians in the middle there, is bigger than some large chunk of the input and smaller than some large chunk of the input, right? And we're being conservative. So we want to figure out which of these squares are definitely, let's say, first start with smaller. Okay. So in this picture, which of these are definitely smaller than the purple? Yeah. Oh, top left. Oh, like here. Ah, okay. So all of this, well, first, this is all clearly smaller because they're smaller within the green. Okay. And then everything up above is also smaller because we're vertically sorted as well. Okay. And roughly how much of this input does this represent? Sorry? Uh, a quarter. Actually more. Yeah. Yeah, so in this direction, you're getting half of the columns, and in this direction, you're getting 3/5 of the rows. So overall, you're going to get, 3/10 of the input. Okay, so you get 3/10 then. So a little better than quarter, and we're fighting for those things because it's going to help us in the recurrence. Okay, so the other side might be easier now. Which are the squares are definitely bigger? Yeah, the bottom right. So I guess if you're going slowly, first the things going to the right are clearly bigger, and everything underneath those are definitely bigger. Okay. And then again, roughly how much does this represent? Like, yeah, roughly 3/10. The only thing slightly misleading about this picture is that, the last column, might only have like one element or something in it. So, you know, maybe you subtract four or something, but that's not a big deal. Because the input might not be cleanly divisible by five. You might have this left over of one or two or three. Yeah.
So if array A is like randomly organized, how can we put it inside a square?
So this is only for the proof that I've sorted things. So it's easy to visualize the 3n/10 that's smaller and the 3n/10 that's bigger.
So does that mean you have to sort all medians?
Okay, so the median of medians, how do we get it? Recursion. So the answer is we don't have to sort it. It's just in the proof, I just want to give a visual picture so we can just like literally see and count it. So in the proof, I can rearrange it so it's easier for us to see what's going on. But the algorithm doesn't have to do this, right? The algorithm just assembles green and then finds purple recursively. It never consciously sorts the left and sorts the right. Okay. Yeah. So yeah, there can be gaps between kind of what we prove and what the algorithm does. We can do more work on the proof side without making the algorithm slower. All right, other questions? Okay, so that's that. Okay, so now if I wanted to model the running time of this algorithm, I get the median of medians, and I know that my rank is going to be between 3n/10 and 7n/10-ish. Okay, so putting that together, I'm looking at the bottom left here. How would I first model the recurrence, the running time recursively? Oh, oh no, actually, just for this subroutine, the median and median. So I get the what's the running time for just this subroutine we analyzed? Yeah, basically Tn/5 is the main recursive call, but we also do a little bit of extra work. Plus O of n. Something like this. So this in Tn/5 plus O of n time, we now get something that's between 30% and 70%. That's better than 10%. Yeah. Well, for example, the first part where you get a median from every group of five. So you're really looking at your entire input. You look at these five, you look at those five, you look at those five, you look at those five. Okay. But that first suggestion from before was to take an arbitrary 20% and find a median. that only returns something that'll be between rank n over 10 and 9n over 10. Now we got it up to 3n over 10 and 7n over 10. So we're able to chop off a lot more input. But the running time is still the same. In both cases, we were looking at 20% of the input, basically. Recursing on 20% of the input. Okay, good. So we can plug that in to our algorithm, right? So now I'm going to median the medians to get my pivot. And then I'll calculate its rank again. I'll compare everything and recurse on the appropriate side. Okay, so just like before, but we have this more sophisticated routine to give us the approximate median. It's going to be a better approximation. Okay, so correctness is not an issue. The only question is running time. Okay, so let's first come up with the whole recurrence and then solve it. So what would be the recurrence? I don't know if it helps for me to show this instead. Maybe I can zoom out a little. So anyone want to propose a recursive formula for T of n? Yeah. Yeah, so now you're guaranteed something between 30 and 70%. So you're always throwing away 70% of the input. So our second recursive call is now 7n over 10. It used to be 9n over 10 plus the big O of n. Okay. So if I go to the recurrence tree, I have input of size n, and down here we'll have input of size n over 5, input of size 7n over 10, n over 5 squared, 25, I guess. It always gets harder. 7n over 50, 7n over 50, 49n over 100. This is just multiplying numbers, right? Okay. So if I look at the total work on the top level, what would that be? And yeah, not a trick question. Okay, what about the second level? Yeah, 9n over 10. We can write 9, 10. You can also think of that as 1/5 plus 7 over 10. N. Okay. What about this next level? It's just going to square it. So that'll be 9 over 10 squared. Or it might be easier to visualize that in the tree as 1/5 plus 7/10 squared times n. Okay. So then you imagine the next level is going to be cubed and fourth and things like this. Okay. So that means when we add everything together, you're going to get something like, you can go to infinity, 9/10 to the I times n. Okay. What does this all come out to? Sorry? O of n. Okay. So the key thing is we got this kind of n/5 plus 7n over 10 to get under 1. Then you have your geometrically decreasing sequence and you just win. Right, very clever algorithm. We won't put a question like that on the exam or something. Right? It's very nice. Okay. Any questions? Yeah. Yeah, so the question was for median and medians, why was it n over 5? I can open this up to the floor. Why was it n over 5? Where did the n over 5 come from? Yeah. That's right. So if we remember how we assembled green, it was from first grouping our input into groups of 5, partitioning it into groups of 5. For every group of 5, we got the median of that. So every 5 we pulled out 1. Every 5 we pulled out 1. Every 5 we pulled out 1. Yes.
The 7n over 10.
Oh, where did the 7n over 10 come from? Where did the 7n over 10 come from? Yeah. So what we showed here is that the rank of our approximate median is always between 30% and 70%. So like in an extreme case, it's exactly 30%, and you have to recurse on the big side. And the big side will have 7n over 10 input. So 7n over 10 is that second recursive call where our approximate median isn't quite down the middle, but it's enough to throw away at least 3/10. And in the worst case, you're keeping on to 7n over 10. 7n over 10 is the second recursive call. Yeah. Does it have to be groups of 5? Or what do you all think? Yeah.
It's the best. If you make it bigger, you don't get as much like 9 and if you make it third, you don't get like exactly 10 log n again if you don't speed that up.
Yeah, okay, so this is a famous thing. If we actually went down to n over 3 and you work through it, you're actually not going to get the full win. It's the way it's going to work out is you're going to get something where you basically spend n on each level and you get n log n overall. If you had done 7, then you will get something that adds up to less than 1. You'll get a geometrically decreasing sequence, although it'll be a little bit bigger than 9/10 is what we got. It'll be a little bit, so if you cared for constants, that constant will be a little bit bigger. Yeah. So in fact, if you do bigger, I think it'll always be okay. But if you go down to 3, it won't work. And people used to be very excited about this algorithm and they would kind of play with all these. It's been 50 years, but yeah. Yeah.
So like, how is this better than like just doing with the median? Because like the median also gives like all right.
Uh, w- ah, oh, so okay. Why is this better than median? The only issue is we don't have median. I just put that there, say, oh, imagine we had median just to help develop some ideas at the beginning, but eventually we just filled it in here. We relaxed that to an approximate median first, saw that, oh, that's kind of okay, and then finally we supplied the approximate median here. Yeah.
Is it possible that like in practice your constant factor for like this algorithm with O would be so high that it worse than n log n? Because I feel
Ah.
like
So this is actually not the yeah great algorithm in practice. People do complain about the constant. Uh, there's a very slick algorithm we're going to do later that's almost more intuitive. The only thing is that it's randomized. In some ways, it has some similar ideas. Anyone want to guess? Like imagine you're kind of thinking heuristically. Don't worry about proving anything probabilistically. We'll do that at the end.
you just keep picking like random every time.
So if you pick a random pivot, you're kind of hoping it's close to the middle, right? For example, we know that if you get something within the middle 80%, you're done, right? Well, there's an 80% chance it's somewhere in the middle. Right, so you could even a more clumsy algorithm is you just pick a random one, see if it's in the middle 80%, just compare everything. If it is, then you're happy, you're done. If it's not, just throw it away, try again. Next time you're hoping to get it right. So you're just kind of flipping coins until you get a heads, and this coin comes up heads 4/5 of the time. In general, like for example, even coin, where 50%. How many times do you expect to flip before you get a heads? An expectation on average. How many times do I have to keep flipping until I get a heads? The answer is 2. If coin flipped heads is probability 25%, 1 in 4, how many times on average do I have to flip? 4. So in general, it's always here. Actually, it's 80% heads. So you're flipping like 5/4 times on average to get a head. So you're probably going to get a heads, and each time you get a head, you're going to chop away at the input a lot, and then you can carry that through. Okay. And then I mean, I'm sure many of you have already done quite a bit of probability, maybe in your statistics classes. Yeah. Why is 5 magic? I think here you just work it out. I haven't done it in a while. So you'll try n over 3, you'll find it doesn't work. And even numbers are awkward because like, what's the median of even numbers? So you just jump to 7 and it's like, it got worse. And you try 9, it gets worse. You could probably write a closed form, as a function of your value k or h or parameter. It's getting worse. It's always below 1, but it's converging to 1 or something. Is what I think is probably going on. Yeah.
Just to understand, what happens if you just break it up into 2, right? Just like 2 halves, and you did that. Technically, each time you would remove half of the array. So like, why is that?
Okay. Maybe I can recurse on both sides and get the median of each or something like this. Well, I don't have a great answer. Again, a free country, you can do anything, but breaking in half starts to look a little bit merge sorty. There we broke in half, we solved the 2 problems exactly, and then we combined it in linear time. And at the very least, I imagine getting a median from each side, and then maybe whatever candidates you get, you'll have to compare to everyone. and suddenly you're looking almost exactly at the same recurrence as merge sort. You broke it in half, you did something exactly, and then you spent O of n time, that's going to give you n log n. So maybe there's something else you can do besides that, but at least the first thing that comes to mind is going to give you n log n instead of n. Yeah.
Maybe with this groups of 5 and constant time or of n.
So each group of 5 can be done in constant time, but then yeah, so you spend O of n time. Well, you have 5 elements.
Just write like hard.
Yeah, you can do anything you want. Yeah. The key point is it's independent of n. Once it's independent of n, then you can get away with anything. You can just sort it, you can hard code it. You can just try each one and see if it is the median. You can do anything you want. Probably come out a constant. Yeah.
If you're recursively running median of median, like once, like if you run it on A and then you get C and you run it on B, how do you guarantee that the pivot is perfect?
Yeah. Okay, so if you recursively run median to medians, how do you guarantee anything? So we should be careful here. First, we get the subarray of medians. Then we get the exact median of the subarray. So we're not getting an approximate median of this one. We're getting an exact median of this green one.
That could be done in O. That could be done in O of n.
Well, it's done with a recursive call. So we're implementing select, right? So among other things, select does median exactly. So here I'm calling select on an input of size n over 5 to get the exact one. So if we look at our overall recurrence, okay. So we look at our overall recurrence, this is to implement select, right? So I want to select an arbitrary thing. The Tn over 5 comes from, I first get that sub green array of size n over 5, and then I use myself recursively to get the exact median. So I'm getting the exact median of this sort of representative sample of n over 5. So the only loss is coming from the initial step going from red to green. I do the green part exactly. And that let us, argue with precision, this kind of argument here. I do know that I have the exact median of the green. And at the very least, I'm always at least 3 and over 10 on each side. So we're not recursively getting approximate medians. It's just the approximate median is using exact median over a smaller input. Yeah, it's a bit subtle. Yeah.
Doing recursive on this step, then how can the time complexity of this be T of n will be as a slow event? Because they're not using it. Assuming
Okay, so the median, if T of n represents calling select on an input of size n, the median still first spends big O of n time assembling the green, and then you do your exact algorithm on n over 5. Right, so I think maybe one source of confusion here is that there's two different things going on. One is we're getting an approximate median, but then we're using exact, right? And maybe it seems more confusing because in the approximate median you use to implement exact. But I think here this is where you want to take the leap of faith of recursion, right? So ultimately the whole thing comes down to you have this getting the exact median over that smaller set of n over 5, and it's going to return exact median by induction. And then you're going to use that as a pivot to then get you a subset of size 7n over 10, and then you'll get what you're looking for by induction. So some level, as long as the input's smaller, because we wrote the recursive spec, right? So we know what we get. So just trust it. Then it's okay. Yeah, so it's not as homogeneous a recursion as before. Yeah.
So, question here.
Another question.
You scroll back slide to the green there. So is that right? Now I'm wondering when you have the green and you create other lists from them, they're more or less sorted. They're not exactly sorted, but they're more or less, right? With save time with building up.
So what do you know about n over 5? You don't know that when you first assemble the green, it's sorted at all, because it's that's just coming from red. So I don't think you have too much information.
Just
It's just broken. It's just filtered down. Yeah, I don't think there's much structure there. Plus, we have a O of n time. What more do you want? We're not going to beat O of n. Like, just, you know, what you want to do is just move on to more interesting problems, I think, once you have a satisfying solution. Yeah. Besides, the random one is the one you should be doing. We just don't have the dexterity to analyze that yet. All right, other questions. It's a very beautiful algorithm. I think it actually, was very influential because it's highly much more non-trivial than merge sort, right? Because it is kind of non-homogeneous recursion. Okay. Good. I don't want to, last time we went a little long and I could just see like broken hearts in your eyes. So I want to finish on time. Okay, so here's the second and only remaining problem of the day. It's going to be divide and conquer again, but be a different flavor because this will be a geometric problem. So I'm going to give you a set of points in the plane, and your goal is to just find the minimum distance between any 2 points. What's the closest one, right? You can imagine. I don't know what you'd imagine. Okay, so like here, I don't know. Assuming like this, whatever the distance on the whiteboard, then like maybe I'm not sure. What's the closest distance? It's kind of ambiguous. Oh yeah, what are you pointing to? The right side, top right? You think this one? Or this one? Or this one?
I think that's pretty cool. They're calling 106.
They were called, I drew this. I'm not that lazy. Plus, like, I wouldn't like someone rotate. I mean, yeah. Anyways, it's not that hard to draw dots. Like, I'll draw one more for you. See, okay. All right. So this is the closest pair. Now, what would be the obvious algorithm in running time? N squared, right? So I can compare. I don't want to do that. I can compare every pair and do it N squared time. But of course, that's sort of excessive. Like, for example, you can look at this picture and be like, well, the 2 farthest points, I should never bother comparing and things like this, right? So the question is, can you do better? Okay. So, okay. Yeah, I've tried to set up in a way to see if we can guess it. It's always a little awkward, but let's see. Okay. Suppose this is a slightly misleading picture because they're not necessarily sorted as your input. Yeah. Oh, okay. If you break it up into thirds, this is a fun idea. Okay, so if I break it up into thirds, so maybe I can just sort by x coordinate or something and break it up into thirds. Then at some level, like I know, actually, do I know? Well, I guess once you might have to be a little bit careful about y coordinates. But let's at least go through the intuition. The idea is I could break it up into thirds and make a recurse on this side or something, 1 set of 2/3, and I can recurse on this side or something. And then I can try to say, well, I don't really need to compare these two because it's going across a big gap. Okay, now that makes sense. It definitely has divide and conquer feel. I think there is a subtle bug here. I think it can actually go across the gap, but in like what kind of scenario? This picture doesn't really reflect it. Yeah. Oh, that's an easier example. If there's nothing in the middle, then it's definitely got to go across the middle.
It's like separated by the line system.
Yeah, so here we're kind of compressed in landscape form, but if the y coordinates are really big, then you might actually want to go across the middle because the y coordinates are matching, whereas on the same side, the y coordinates are massively far apart. But this is actually a good idea because actually I didn't really see why that was flawed at first. This is an interesting idea. Okay, so that's one divide and conquer that actually has good intuition in my mind, but didn't quite work. Anyone want to suggest anything else? Yeah. Can you recurse on both x and y? Again, it's free country, but what do you mean? Oh, you could do it on x and you could do it on y. So in my worst case, when the y's are really bad, that'll capture it later. Well, I'm worried about like now the diagonals are being bad or something like this. It's not obvious to me. Yeah. I'm not sure if just doing it in both directions will solve it. Plus, there might be another issue where, you recurse, say, with on the x, you do the x version, right? And now in your recursive subproblem, do you do x and y? because then your recursion tree is going to start branching out. Maybe you don't have to, but that'll still require some justification. Yeah.
Next version, you do like the top right quadrant, the top left quadrant. Then
Oh, can we start maybe dividing into quadrants? Or ninths? I don't know. At least I can draw it. And now you're saying like, well, maybe I don't have to do this comparison or something. But again, I think there's still this issue of like empty cells seem to always be an issue. So I'm a little worried about that. Yeah.
You could probably make the sectioning dynamic based on number of that is in there.
Well, this could still be dynamic. I mean, I can do like, yeah, I can. Let's say they're still roughly equal, but there may still be holes in the middle, right? Because
That wouldn't be a sector. Like you would like do the sectioning and reporting for like
okay, so now you're imagining like some kind of binary partition thing where I first try to divide in half and then divide in half and recurse on both sides. Well, maybe that's actually not so dissimilar to, okay. So, but this is more dividing in half at a time, not necessarily dividing with buffer in the middle, which was maybe a one characteristic of the original n/3. Okay. So, okay, then maybe I can skip some of my silly, well, any other fun examples? Because this might be somewhat similar. Yeah.
maybe if you divide the entire like if you imagine like a lot of points, you divide the thing into a grid. You can divide like the entire like space into a grid,
Uh-huh.
and then with that. Okay, if you have a grid, if you can have like almost like an area of like or like you only know that then all the points in there, you would only have to check that grid and maybe like the surrounding time.
Okay, so if you had like a fixed bounding box, like everything was let's say that everything was between 0, 0 and 1, 1. And you were just promised, because there's only so many pixels on a page or something, that there's some minimum possible distance of like delta 0. Then you could imagine trying to do divide and conquer where I keep decreasing the area, you know, I might divide into 4, right? And divide into 4 and divide into 4 and things like this. And then say, well, once I get the squares like much smaller than delta 0, there's no point in going further or something, because that's like some minimum resolution. Okay, and you can do something like this when you have this sort of fixed ratio between the maximum and the minimum, which might often be the case in practice. But we're not going to assume that here. So there could be a so if you kept dividing in half until you got down to your minimum distance of delta 0, let's say you started the minimum, it was first a 1 by 1 squared, gets all the way down to like delta 0 by delta 0 squared. Then you're going to need something like log of 1 over delta 0 of this depth in the tree. Okay, so it's some parameter based on the ratio of, you know, the resolution. But I want to do something that doesn't depend on this resolution ratio. So this will work if this was kind of fixed, or something. You can go in this direction if this resolution was bounded. But I'm not going to assume that to be the case here. I want to get sort of a resolution independent, so to speak, algorithm. But it is a good idea, and one that shows up for a lot of problems like this. And sometimes it's preferred in practice because you do have this bounded ratio. Okay. These are all very good ideas, actually. Any other good ideas? Oh, okay, we have 2 more. Yeah, let's start in the back. You can use a quadtree. Yeah, okay. You can use an off-the-shelf algorithm to solve this problem, and then you can solve this problem. Okay, anyone think from first principles? Yeah.
Like someone else said, like you're dividing into like portions. Like
Huh?
you said like something about like there's gonna be a gap in the middle, so you would have to check points that like on both sides, but there's only so many points. I guess that you'd have to check on both sides because obviously like if you have like all the way to the right and all the way to the left, you don't need to check that if you're like by at least like X distance, right?
Okay, so if I am doing something where I'm dividing things in half, maybe here's some, you know, I divide things in half, I kind of recurse, and maybe you're hoping, okay, so you haven't done anything about the crosspairs at this point, right? But maybe we can try to argue that we only have to look at a limited number of crosspairs. At least intuitively, it should be the ones that are closest to the line. And hopefully you can dismiss things that are very far away. So in fact, this is the approach we're going to take. Okay, but we have to sharpen that and really be able to argue that's going to be the case. Given that is what direction we're going to go, does anyone want to suggest anything else? Too late. Okay. All right. So, okay. So I'll skip this. You know, if it was, well, I was going to warm up saying, what if it was one dimension? The first thing you might do is sorting and just scanning. Yeah, but what we're going to do, screw this. Okay. All right. So let's take this last hack. Okay. So what we're going to do is this kind of algorithm. So first, I'm going to basically split at the median x coordinate. Okay. So I might, oh man, I might look at my input. Okay, and I figure out like the median x coordinates that I splits the input in half. We can even use the algorithm we just did. Okay. And now what? This next step is guessable. Sorry? Yeah, they're split. Now they're split. What do you do? Yeah. Or recurse on each half. Okay. Crude tricks don't work sometimes. Okay. So you're going to recurse on both halves, and that's going to tell you, okay, maybe that's the smallest one over there. That's the smallest one over there. Here's some delta prime. You can compare the two and say, at least if I'm only looking on the two halves, then this is the smallest. Okay. Now, all you're missing is the cross pairs, right? I haven't compared any point up from the left to points on the right. So now we just need to compare those. Okay. Now, one thing to point out is that all I'm worried about now is seeing if I can beat that minimum distance from either side, right? So in particular, there's no point in me going out further than delta units from the median. Okay. So I can kind of draw this line, which is supposed to be delta far away from that median. Okay, so whatever that minimum distance you found on the other side, I know that I only have to look at points inside here because anything outside these two sides is going to definitely be more than delta. So even if, or inside here to outside here, you don't need to do. Inside here to outside there, you don't need to do. Because the x will already give you delta. Okay, because we're only trying to beat delta at this point. So now you can imagine just going down this narrow thing and doing those comparisons. Okay. Now, as drawn here, it looks pretty thin. Like there's a lot less points in the middle, right? And okay, so let's see. What is drawn? Okay, so yeah, we're gonna look at this vertical band with two delta on either side around the median, and we're gonna compute the minimum distance inside the band. So that's the high level thing. But now I want to try to argue that this part can be done very fast. Okay, I mean, here it doesn't look like there's many points inside, but maybe there's many points inside. Okay, so I'll keep it moving. Okay, so some basic observation about what's going on inside this band, right? We just have to get those pairs that are inside this narrow band. Okay, so okay, it's very narrow. That's the first observation. The next observation is okay. Any pair of points on the left side, of course, have minimum distance at least delta. Is that the same on the right side? Okay. Okay, so you're looking at this thing of like width delta, right? And I could divide this into half. And meanwhile, any 2 points on the left side have to be delta apart. Any 2 points on the right side have to be delta apart, right? So at some level, it's saying you can't stuff that many points inside here, at least within some vertical block, right? I also don't need to compare things that are more than delta units away on the y coordinate, right? So if I'm looking at some like delta or 2 delta vertical range, maybe there's only so many points that can even be in there. That's starting to suggest that this point here may only need to be compared to a limited number of points on the other side. Okay, so we can make this a little bit more formal. Okay, so let me first then explain the algorithm and then we'll justify it. So as usual, this looks more complicated than you should be. So I get the median x coordinate and then I split the input in half. I get the minimum distance on the left, the minimum distance on the right. And that gives me some delta. That's the minimum on either side. All right. Then I'm going to assemble all the points that are within, their x coordinate is within delta of that median x. Okay, so now I'm just assembling the band. That's some linear time to just check everything. Okay. Now, here's the key point. So I'm going to sort everything in decreasing order of y coordinate. Okay, so I'm going to go from top to bottom. And here's a nice thing. I claim that, the first point only needs to be compared to the next 10. It doesn't have to compare to all of them in the band. The second point only needs to get compared to the next 10. The third point only needs to get compared to the next 10. Each point only needs to get compared to a limited number of points in the band. And I'm claiming that's sufficient. You can see why that's useful, because then you don't have to do n-squared comparisons in the band, right? Each one only gets compared to 10. Question though is why? As some of we've already kind of discussed the intuition, there should only be so many kind of nearby, and 10 should be enough. Okay. So then the sufficient lemma, let me read it slowly, would be the following. So let's say I'm looking at like some square. So if I'm like, if I'm from the vantage point of some point here, okay, and I kind of know I'm only trying to beat delta distance. So maybe this is the original median, and I'm only trying to beat delta, right? So I know there's really no point in going past, delta units away. So what I want to do is I want to show that there can only be a limited number of other points sort of in this 2 delta wide, 1 delta down rectangle. And if I can show that, let's say there's at most 10 other points in this square, then by just making sure I compare this to the next 10, I'll cover everything in this region, including some wasteful things on the left, but that's okay. 10 is enough. But to that end, I need to show there can only be 10, at most 10 points in this rectangle. Does the motivation make sense? Okay, so as I'm marching down, I have my point here. There's no reason to go past delta because I'm only looking for distances less than delta. And then this 2 delta here is the left and the right, because I assembled P3 where I just threw everything together. Okay, that means it's going to make some unnecessary comparisons on the left. I don't care. It's not that much anyway. But what I want to argue is that there can only be a small number of other points in this square, less than 10, so that if I looked at the next 10, it'll cover everything in this square. Okay, so why? You don't have to be, precise at first. We'll make it more formal in a moment. But maybe intuitively, why? So these points need to be somewhat far apart, right? Because the minimum distance is delta. So over here at most delta, delta or something like this. So they have to be kind of spread out. You can only cram so many in before that distance gets to be less than delta. Okay, so just because they're delta apart, you can only fit so many in. So I think that's the intuition. There's 100 different ways to prove this, or get it written down basically. At some level, we sort of morally proved it. But to get it down explicitly, what's one way to make this precise and explicit? It's really more just kind of an elementary geometry problem. It's not really an algorithm problem anymore. Yeah.
Maximum, minimum, distance between them is delta over.
Okay.
Distance between the closest, most delta over 5. So they were all delta over 5. Span rectangle. And so it's the same over there.
But in fact, it's the x dis. Oh, their opposite sides is still over 5 over 5. Okay, so even within one square here, you're saying like this has to, if I kind of put them really far apart, I still have to at least be making progress. Okay, I think that'll be okay. Let me give a different formulation that I think is easy to at least verify and get written down. I'll do it quickly in the interest of time. So if they're all delta over 2 delta apart, you can imagine drawing a circle of radius delta over 2 around each point. Okay, so the radius, it's not a perfect picture, but the radius is delta over 2 of these circles that are centered at each of the points in your square. And since all the points are delta apart, the circles won't be overlapping, right? They'll always be disjoint. So you have all these squares. Sorry. Okay. So we have you can wrap them all in these circles of radius delta over 2, and these are all interior disjoint circles, and they're all taking up some area, right? Like pi times delta over 2 squared or something. And it's all different area because they're disjoint. Meanwhile, they all fit in this, slightly larger square where I add delta over 2 on each side. Okay, so this rectangle is like maybe 2 delta times 3 delta, so like 6 delta squared total radius or something, or total area. And each of these points, kind of reserves for itself an area of whatever delta over 2 squared times pi. Okay, so you can only fit so many in until all the area is taken up. So in other words, each one constitutes some area, delta squared over 2 times, or delta squared over 4 times pi, and they're all eating up out of this 2 delta times 3 delta rectangle. So this is called a packing argument of kind of volumetric or area-wise packing argument. Each of these things take up a certain amount of area or volume, and you can only stuff so many in. So of course, I think intuitively you all kind of saw what the goal was to prove, but that's one way to get it down on paper. Okay, so the running time will be very fast. So that's the lemma. It's gone a little bit more slowly in the notes. In general, my goal in the lecture is to make sure we get the main ideas, knowing that we're always backed by much more slowly formally written notes. Now, when we do the running time, and this is where we're almost done, who wants to at least just model the running time, and then we're basically out of here? Yeah.
2t n over 2.
All right, 2t n over 2 plus big O of n. We split the input in half, we recurse. And the nice thing is each point in the middle only gets compared to 10 others, not the whole thing now. That's why it's big O of n and not n squared here. And then we've seen this running time before, so what does it come out to? N log n. This is the exact same as merge sort, so I won't do the recursion tree again. So you get n log n. Okay, so that's it for today. Next time we're going to try to multiply integers together faster than whatever you did in elementary school.